Um, Hi, Professor. Life or death for a young child often depends on whether he or she is born in a country where vaccines are available or not. And the availability of vaccination majorly depends on the logistics. Today, we are going to present a model that has been developed by our team to aid in the prioritization and distribution of vaccine purchase orders. This project is done as a requirement for the systems modeling and optimization course and is prepared by Sri, Catherine, and Ketan. So, so the agenda for today's presentation is we'll go with the problem description and define the model objectives and approach. For the prioritization and optimization models, the modeling, assumptions, implementation, and outcome will be discussed and presented. The integration of the models into a final script will be discussed, and finally, we will state our conclusions with recommendations for the future work. Now, vaccines deliver antigens to individuals, which allows the body to trigger an immune response to fight off certain diseases. Vaccines are life saving, but due to supply shortages and scheduling difficulties, they are not available to everyone that needs them. More than 2 million children die every year due to lack of vaccination. In 2019, 20 million children did not receive the measles, diphtheria, and tetanus vaccines as depicted in the figures on the right. Currently, vaccination averts 2 to 3 million child deaths each year. The model we propose is intended to efficiently prioritize and schedule vaccine distribution such that a maximum amount of children receive these life saving vaccines. Around 19.7 million children under the age of 1 do not receive the vaccines they need. This is often due to the lack of supply availability, weak cold chain systems, and poor supply chain management. These issues are very prevalent in low and lower middle income countries. They are depicted in the figures on the right. This shows that it is impossible to vaccine children without adequate supplies of vaccine at service delivery levels. Given that the initial stock is available, our model will help prioritize and schedule these deliveries. Now, the objective for this project was to develop a model that would improve the supply chain logistics process for efficient vaccine management. Our final present recommendation are in two parts. The first provides an optimized solution to UNICEF for prioritizing the vaccine purchase orders that need to be shipped in any given week. And the second provides an optimized model for the delivery schedule for the prioritized orders based on available flight information. A high-level description and process flow chart of the model can be seen here. The prioritization model reads input data from each purchase orders and then generates a prioritized purchase order list. Then the scheduling model reads the prioritized list and the flight information and generates a schedule for the distribution of vaccines in the given week. Sorry. Now, for this project, we decided to use the data envelopment analysis, abbreviated as DEA, to determine the priority of each purchase order. In the DEA model, the objective function is defined as a collection of decision markers. Sorry. DEA defines the weight for each decision marker as no as like decision markers as unknowns and solves for the optimal weights when targeting a specific objective function. In the case of our model, the purchase orders contain the following information, that is, vaccine type, antigen, origin, destination, number of doses, and number of doses per vial, planned week of delivery, inventory at destination country, and change in immunization level at destination country when the purchase order is distributed. One of the limitations of DEA that it does not handle categorical inputs well. For this reason, only the numerical inputs are considered in this model. Advantages of DEA include the simultaneous analysis of outputs and inputs and the ability to know the relative efficiency of any scenario compared to the best observation. Additionally, few assumptions are required for the model. Now, from here on, she would explain you the prioritization model.
The prioritization model uses three sets in the input data. Set P is a list of purchase orders to be prioritized. Set 1 is a list of inputs into the purchase order, which is represented as I. Then set J is a set of outputs or results from the purchase order. In an extended formulation for our particular problem instance, the set of inputs would include number of doses per vial, and planned week of delivery. The outputs include inventory at destination country and change in the level of immunization at destination country when PO is distributed. The decision variables of this model are the weight of each marker, where the markers are all inputs and outputs. The objective of the model is to maximize the summation of the outputs of any PO given static marker weights. This model contains three constraints. The first describes that for every purchase order, the sum of all outputs multiplied by their marker weights minus the sum of all the inputs multiplied by their weights must be less than or equal to 0. The second constraint states that for every purchase order, the sum of all inputs multiplied by their marker weights must equal 1. Lastly, the marker weights should be all greater than or equal to 0. We have made some assumptions, the most important out of which is that the categorical input variables do not significantly affect the prioritization. There is This is the only main assumption. The advantage of this model is also that there are not a lot of assumptions required for DEA. The mathematical model was then translated into a .mode AMPL file as seen here. This model is called along with a dummy dataset using a .run file. The functionality of this module was tested by creating a dummy dataset and running the code in AMPL. The following output was obtained. H is prioritization of each PO, U is the weight of each input variable, and V is the weight of each output variable. A weight between 0 and 1 was applied to each decision marker as determined by the solution, which maximizes the objective function. We recognize from more testing with a greater number of purchase orders and their decision markers that DEA performs better when there is more variation within the decision markers. That being said, the snippet here only has two purchase orders as the code has been integrated with scheduling and we have just two purchase orders to demonstrate the scheduling aspect. So talking about the data consideration, we have a few inputs and outputs. So out of it, input 1 is the number of vials purchased. Input 2 is the number of doses which must be administered to achieve immunization from the disease. Common vaccines like the DTaP require 4 doses, hepatitis B and rotavirus 3, but influenza, MMR, etc. require just 1 dose. So the most common numbers vary between 1 to 4. The third input is doses per vial. It is common to have multi-dose vials, and this is preferred by countries or institutions that immunize a large number of people at once, like when there is a polio vaccine drive or immunizing a whole community against a communicable disease that is prevalent when there is an outbreak. Sparsely populated regions usually prefer single dose vials because many vaccines have to be administered within 8 hours of breaking the seal of the vaccine. So we have taken some of the common values like 10 doses in a multi-vial and single vial doses. The fourth input is the cold chain capacity. This usually refers to the availability of proper storage for the vaccine. The input, though, takes into consideration the time for which the vaccine can be in transit without being in prescribed condition for the vaccine in the storage location. There are particular conditions which have to be followed even while it is in transit. Even when those conditions are maintained, these vaccines can be in transit only for some time. Like the varicella can be in transit only for 72 hours, while many other vaccines need to be delivered within 8 to 10 hours, and some can last up to 7 days. Now, moving on to the outputs. Output 1 is the percentage change in immunization that can be achieved after the PO is delivered. Immunization level is represented as percentage by WHO, hence, the value can vary between 1 to 100. Output 2 is past due, which takes into consideration how late the PO is being delivered in weeks. Then output 3 is the inventory that is depleted. That is, it refers to the available space in the storage location to accommodate the new PO that is being delivered. The PO, which makes a considerable change in the immunization level prevalent in the location where it is being delivered, replenishes the inventory with a large capacity. That is, an inventory that is completely depleted and is long overdue has higher priority. This essentially ensures that the PO are delivered to make maximum impact. The model also gives high priority to vaccines that need lesser number of doses to achieve larger change in immunization level. Since the model has an implicit tendency to minimize the inputs, the model has a tendency to give higher priority to vaccines that are delivered as single doses, but such factors come into play only when there are two POs with comparable change in immunization level. The budget would be a constraint in the scheduling, and that would take care of this problem as multi-vials are cheaper than single vials and require less space for storage and transport. Now I'll hand the presentation over to Catherine. Thank you.
The scheduling model uses three sets in the input data. Set N is a list of all the cities in the system. Set A is a list of all the available flights between two cities, and set P is a list of prioritized purchase orders. There are many parameters to describe the data in these sets. For each flight, I and J and A, there is a fixed cost of scheduling the flight, a variable cost of scheduling the flight dependent on the amount of vials on that flight, an amount of time for the flight to be completed, and a maximum amount of vials which can be sent on that flight. For each purchase order, there is a cold chain capacity limit, a demand at the destination city, and a priority. Finally, there is a maximum weekly budget for scheduling these flights. The objective of this model is to minimize the amount of money spent on scheduling all flights. This is a combination of both the fixed and variable flight costs. The amount of money to schedule a high priority flight is scaled down to give it more weight and a higher likelihood of being scheduled. This model contains 6 constraints. The first and second constraints describe that for every city, the amount of vials entering the city minus the amount of vials leaving the city must equal the demand of that city. The third and sixth constraints deal with capacity, in that for each flight, the amount sent must be less than or equal to the flight's capacity. The fourth constraint says for every purchase order and flight, the time spent on that flight must be less than or equal to the cold chain capacity limit for that purchase order. Lastly, the amount of money spent scheduling these flights should be less than or equal to the weekly budget. Similarly to the prioritization model, the scheduling model has only two assumptions. The first is that all cities are transshipment nodes, meaning that inventory can be both incoming and outgoing. Second, if a purchase order is not scheduled due to constraining resources, it will be added to the purchase order list for the following week. In subsequent weeks, it will be given a higher priority because the planned week of delivery will be further and further past the current date. The mathematical model was then translated into a .mod AMPL file as seen here. This model is called along with a dummy dataset using a .run file. The functionality of this module was tested by creating a dummy dataset and running the code in AMPL. We tested this module with several different datasets wherein it was possible for all, some, or none of the POs to be determined based on the available flights. Pictured here is the scenario where all POs can be delivered since the weekly budget is extremely large and therefore non limiting. The two modules, prioritization and scheduling, have been integrated into one .mod file. Here, prioritization is called first as problem 1, taking inputs of the available purchase order information. The outcome of the prioritization is set as a parameter in the .run file for problem 2, which is the scheduling module. Problem 2 also takes the input of the available flight information. This model is already functional within one file. For deploying the solution to UNICEF or other organizations, this file could be converted into an executable using Python or a similar language, which would allow the user to utilize the solution without requiring they had AMPL installed. In conclusion, our model efficiently integrates the two modules to accomplish the prioritization and scheduling of vaccine distribution. Using dummy datasets, our model was available to develop or was able to develop a schedule for vaccine delivery in 0.0059 seconds. The strength of our model is that it is fairly generalized and few assumptions were required to construct it. The main limitation of our model comes from our use of DEA in the prioritization module. Since categorical variables were not considered, this model may not provide the most accurate prioritization. We recommend that other model approaches are considered for this module, which are more inclusive of all input variable types.
Now, for the future scope, since this model is developed only for 1 week, it can be extended and developed further for multiple weeks. At the end of 1 week, the data for the next week would be updated to include the POs that have not been delivered. Also, the model can be further developed to include delivery with multiple flights to different purchase order destinations. And the DEA model can be extended to include other criteria in prioritization. These are references that we used along for developing and formulating our models. Thank you.